You were told the universe makes sense, that everything out there follows rules we've already figured out, that with enough math, enough observation, enough time, we've finally decoded reality itself. It feels stable, predictable, complete. But what if that feeling is an illusion? What if the deeper we look, the less things actually fit together? Because right now, something doesn't add up. Not in a small way, not in a we need better tools kind of way, in a way that forces us to question whether we've been understanding the universe correctly at all. Here's the problem. The most advanced measurements we've ever made are telling us two completely different stories about the same universe. Not similar, not close, fundamentally different. And the strangest part is, both of them appear to be correct. That shouldn't be possible. Science depends on consistency. If two independent methods measure the same thing, they should agree. That's the foundation of how we build knowledge. But in this case, they don't. And no one has been able to fix it. For a long time, this wasn't obvious. Everything seemed to be working. The equations lined up. The predictions matched observations. It looked like we had finally reached a point where the universe was no longer mysterious, just complicated. Like a puzzle we had already solved, just needing to fill in the details. But then we measured one number, just one, and suddenly the entire picture started to crack. This number describes how fast the universe is expanding right now. Not billions of years ago, not in some distant future. Right now, in this exact moment, it sounds simple. Measure it once, confirm it again, done. But that's not what happened. Instead, when we tried to measure it carefully, precisely, using the best tools we have, we got two answers, and they don't match. One says the universe is expanding at one speed. The other says it's expanding significantly faster. The gap between them is too large to ignore, too large to explain away, and too consistent to be random, which means something is wrong, not just with the measurement, but possibly with the way we understand reality itself. For nearly a century, our understanding of the universe has been built on a single framework, a model that ties everything together, from the first moments after the beginning of time to the large-scale structure we see today. It doesn't just describe the universe, it explains it. It tells us how matter formed, how galaxies emerged, how everything evolved into what we observe now. And for decades, this model worked almost perfectly. Every time we pointed a telescope at the sky, the predictions held. The distribution of galaxies matched. The leftover radiation from the early universe matched. Even the relative amounts of elements like hydrogen and helium lined up with what the equations said should exist. It was precise, uncomfortably precise. The kind of precision that makes you feel like you're not just approximating reality, but actually seeing it clearly. Because of that, confidence grew, not slowly but steadily. With every new observation, the idea strengthened that we had finally found the correct description of the cosmos. The universe wasn't random. It wasn't chaotic in the way it first appeared. It followed rules, deep, elegant rules that we could write down, test, and trust. And once you trust something like that, it becomes more than a theory. It becomes the foundation. But foundations only feel solid until something pushes against them. The strange thing is, nothing dramatic triggered this shift. No explosion. No sudden discovery that clearly contradicted everything. Instead, it came from something far more subtle, a measurement that should have been routine, a number that should have confirmed what we already believed, the kind of thing you measure not to question the model, but to refine it. And that's exactly why it was so unsettling. Because when that number came back, it didn't refine anything. It didn't tighten the model or improve its accuracy. It split it. Two different methods, both trusted, both tested, both built on decades of work, produced two different answers, and neither one could be easily dismissed. There was no obvious mistake, no clear flaw, just a quiet, persistent disagreement that refused to go away. At first, it didn't look like a crisis. It looked like noise. But the more precisely we measured, the clearer the contradiction became. And eventually it reached a point where ignoring it was no longer possible. To understand why this is such a big deal, you need to understand what that number actually represents. It's called the expansion rate of the universe. In simple terms, it tells us how fast everything is moving away from everything else. Galaxies aren't just sitting still in space. Space itself is stretching, carrying galaxies along with it. The farther away something is, the faster it appears to move away from us. That relationship can be described with a single number. If that number is correct, it tells us how old the universe is. It tells us how large it is. It tells us how quickly structures like galaxies and stars formed. It even affects our understanding of the invisible forces shaping everything. This isn't just another measurement. It's a key that unlocks the entire timeline of reality. Now here's where things get strange. There are two completely different ways to measure this expansion. The first method looks deep into the past. It observes the oldest light we can detect, a faint glow left over from the early universe. By studying that light, we can reconstruct what the universe was like shortly after it began. Then we take that information, apply the model, and calculate forward to predict how fast the universe should be expanding today. This method is indirect, but incredibly powerful. It's like looking at a baby photo and predicting what the person should look like as an adult. And for a long time it worked beautifully. The number it gives is clean, consistent, and backed by extremely precise data. The second method does something very different. Instead of looking back, it looks around us right now. It measures distances to nearby objects in space, using known patterns in how certain stars behave. Then it steps outward, using those measurements to calculate distances to farther galaxies. At each step, it builds a kind of ladder, extending deeper and deeper into the universe. Once those distances are known, we compare them to how fast those galaxies are moving away. And from that, we calculate the expansion rate directly. No assumptions about the early universe. No projections forward, just measurement. And this is where the contradiction appears. Because these two methods, both precise, both trusted, both tested over decades, do not agree, not even close. At first glance, the difference between these two measurements might not sound dramatic. One number is slightly lower, the other is slightly higher. If you're not used to thinking in terms of precision, it can feel like a minor disagreement. The kind of thing that happens all the time in science. But this is not that kind of situation. In physics, precision is everything. Measurements are often accurate to within a fraction of a percent. Entire theories stand or fall based on incredibly small differences. So when two independent methods disagree by nearly 10%, that's not a detail you can ignore. That's a signal that something deeper is wrong. To put it into perspective, imagine building a bridge where two engineers calculate the length differently by that margin. One says the structure should be one length, the other says it should be significantly longer. You wouldn't just average the two and hope for the best. You'd stop everything and figure out why they disagree, because one of them, or both, must be missing something critical. Now apply that same logic to the universe itself. If the expansion rate is lower, the universe is older. It has had more time to evolve, more time for galaxies to form, more time for stars to live and die and create the elements we see today. But if the expansion rate is higher, everything compresses. The universe becomes younger. Structures must have formed faster. Processes we thought took billions of years suddenly had far less time to happen. That changes everything. It changes when the first stars ignited. It changes how galaxies assembled. It changes how matter clumped together under gravity. Even the mysterious force driving the expansion, something we still don't fully understand, could behave differently depending on which number is correct. This isn't like adjusting a setting on a machine. It's like discovering that the entire timeline you've been using is off, that the sequence of events leading to everything we see might need to be rewritten. And the most unsettling part is this. No matter which value you choose, something breaks. If you trust the early universe measurement, the present doesn't make sense. If you trust the direct measurement, the past becomes inconsistent. Either way, the model that once seemed complete can no longer explain everything at the same time. Naturally, the first instinct was to assume something had gone wrong, not with the universe, but with us, that somewhere in the process, a small error had slipped in, something subtle, something hidden inside the way we measure distances or interpret light, because that would be the easiest explanation. Fix the mistake, and everything goes back to normal. One of the leading ideas focused on how we observe stars. The method that measures the present relies on tracking specific types of stars whose brightness changes in a predictable way. By comparing how bright they appear to how bright they actually are, we can calculate how far away they are. It's a clever technique and it has worked for decades. But it depends on one critical assumption, that we are measuring those stars cleanly. In reality, space is messy. Stars are not isolated points floating in perfect darkness. They exist in crowded regions filled with dust, gas, and other stars. When we observe them from far away, especially with limited resolution, their light can blend together. Multiple stars can appear as one. And when that happens, the combined light makes them look brighter than they really are. If a star appears brighter, we assume it is closer than it actually is. That small error then propagates outward, affecting every step in the measurement ladder. Distances become slightly shorter. And when distances shrink, the calculated expansion rate increases. Exactly the kind of shift that could explain the discrepancy. So the idea made sense. Maybe the universe wasn't expanding faster. Maybe we were just misreading the signals. But there was only one way to know for sure. We needed to look again with better clarity, with an instrument powerful enough to separate what previously looked blended, to see individual stars where before we saw only a blur. If the error was real, this new level of precision would reveal it. The stars would appear dimmer, the distances would increase, and the expansion rate would drop back into agreement. In other words, the problem would disappear. All we needed was a better view. So that's exactly what we built. The new instrument was designed to see deeper, sharper, and clearer than anything before it. It could look through dust that once blocked our view. It could separate points of light that previously blended together. It could detect details that older systems simply couldn't resolve. If the problem was caused by observational error, this would expose it immediately. The expectation was simple. Once we looked again with better clarity, the stars we had been measuring would no longer appear artificially bright. The blending would disappear. Individual stars would stand out. Distances would stretch to their correct values. And as those distances increased, the calculated expansion rate would drop. Everything would fall back into place. The disagreement would shrink, the numbers would converge, the model would be restored. That was the expectation. So the measurements were repeated. The same stars, the same galaxies, but now with a level of precision that had never been possible before. Each observation was cleaner, each signal more isolated, each source more clearly defined. The noise that once complicated the data was largely removed. And then the results came in. Nothing changed. The stars looked almost exactly the same as before. Their brightness remained consistent. The distances did not increase. The corrections that were supposed to fix the discrepancy simply weren't there. The expansion rate stayed high, exactly where it had been measured before. The supposed error wasn't an error at all. It wasn't hiding in the data. It wasn't caused by limitations in our instruments. It wasn't something that disappeared when we looked more carefully. Instead, it became even more certain. The better we measured, the more confident we became that the disagreement was real. That was the moment everything shifted. Because until then, there was always an escape. A reason to believe that the model was still intact, just slightly misapplied. But now, that explanation was gone. The possibility that this was simply a measurement problem had been pushed aside. What remained was far more unsettling. If the data is correct and the methods are sound, then the issue isn't how we measure the universe. It's how we understand it. And that means the model we trusted for decades might be incomplete. Once that possibility was removed, the situation became far more serious. Before, there was always a sense that the disagreement could be resolved with better data, that eventually, with enough precision, the numbers would align and the model would hold. But now, the opposite was happening. The more precise the measurements became, the stronger the disagreement grew. That changes how you interpret the problem entirely. Because if increasing accuracy doesn't reduce the gap, then the gap isn't caused by error. It's revealing something real, something built into the structure of the universe itself. And that leads to a conclusion that is difficult to accept. The framework we've been using might not be complete, not slightly off, not in need of minor adjustment, fundamentally incomplete. Think about what that means. For decades, we believed we had a reliable map of how the universe works, a set of rules that could take us from the earliest moments all the way to the present. But now, that map is giving conflicting directions. One path leads to one version of reality. Another leads somewhere else entirely, and both paths are supported by evidence. It's like having two clocks that are both perfectly built, both precisely calibrated, but showing different times. You can't fix that by choosing one over the other. You have to question the system that produced them. This is the point where a problem becomes a crisis, because the issue is no longer about measurement. It's about the underlying assumptions, something in the way we think the universe evolves, something in the physics we rely on is missing or incorrect. And until we identify what that is, the contradiction remains. What makes this even more unsettling is that the model still works in many other ways. It still explains a vast range of observations with incredible accuracy. It still predicts patterns we can verify. It hasn't collapsed. It hasn't failed outright. It just doesn't fit everything anymore. And that's the most dangerous situation in science. Not when a theory is clearly wrong, but when it's almost right, close enough to trust, but not complete enough to explain everything, because that's when the cracks are hardest to see and the hardest to fix. As if that wasn't enough, a second problem began to emerge. And in some ways, it was even harder to ignore, because this time, it wasn't about a number. It was about what we were actually seeing. When we look far into space, we're also looking back in time. Light takes time to travel. So the farther away something is, the older the image we see. This allows us to observe the universe as it was billions of years ago. And based on our current understanding, we expect the early universe to look very different from the one we see today. It should be simpler, smaller, less organized. Galaxies, in particular, should be in their infancy. Small collections of stars, still forming, still chaotic. Over time, through gravity and merging, these structures grow larger and more complex. That's the story the model tells. A slow build from simplicity to structure. But when we started observing the early universe with greater detail, that's not what we found. Instead of small, primitive galaxies, we began seeing massive ones, fully formed structures, already containing enormous numbers of stars, not scattered, not incomplete, but organized in ways that suggested maturity. And the timing didn't make sense. These galaxies existed far too early. According to the model, there simply wasn't enough time for them to form. The processes required to build something that large should take billions of years. But here they were, appearing in less than a fraction of that time. It was like discovering a fully grown forest where only seeds should exist. At first, the reaction was disbelief. Maybe the observations were being misinterpreted. Maybe the objects weren't as massive as they appeared. Perhaps there was something about the way their light was being measured that made them look larger or more developed than they really were. That would have been a comforting explanation. Because if the observations were wrong, the model could remain intact. But if the observations were correct, then the problem wasn't just with a single number anymore. It meant that our entire picture of how structure forms in the universe might need to be reconsidered. Eventually, a possible explanation began to take shape. Not all of these early galaxies were as massive as they appeared. Some of them were being distorted by something else entirely. At their centers were extremely active regions where matter was falling inward at incredible speeds. As this material spiraled inward, it heated up, releasing enormous amounts of energy. That energy was emitted as light, a lot of light. From a distance, this extra brightness blended with the light from the stars in the galaxy itself. And because brightness is often used as a proxy for mass, these objects appeared far larger than they actually were. It was like attaching a powerful spotlight to a small structure. From far away, it looks much bigger than it really is. Once this effect was accounted for, some of the most extreme cases began to make sense. The largest, most puzzling galaxies shrank to more reasonable sizes. The data shifted closer to what the model predicted. And for a moment it seemed like the situation might be under control. But not entirely. Even after correcting for these effects, there were still more massive galaxies than expected. Not dramatically more, but enough to matter. Enough to suggest that something was still off. The early universe still appeared to be forming structure faster than it should. And it wasn't just about size. Some of these galaxies showed signs of organization that shouldn't exist so early. Instead of chaotic, irregular shapes, they displayed smoother structures, patterns that usually take long periods of time to develop. It was as if two different versions of the universe were overlapping, one behaving exactly as predicted, the other evolving much faster. That contradiction is difficult to resolve, because it's not a simple error you can correct. It's a pattern that keeps appearing, even after adjustments. And the more data we collect, the more persistent it becomes. Not overwhelming, not enough to completely break the model, but enough to keep pushing against it. At this point, the situation becomes harder to dismiss. We're no longer dealing with isolated anomalies. We're seeing consistent hints that something about the early universe doesn't match our expectations. And when multiple independent observations all point in that direction, it becomes much harder to argue that it's just coincidence. It starts to look like a pattern. And patterns in science usually mean something real is waiting to be understood. So where does this leave us? We have a model that still works remarkably well. It explains a vast range of observations with precision that would have seemed impossible not long ago. It predicts patterns across billions of light years. It describes how matter behaves, how structures form, how the universe evolves. In many ways, it is one of the most successful frameworks ever created. And yet, it doesn't fully fit the data anymore. There are cracks. Not catastrophic ones, not yet, but visible, persistent, refusing to disappear even as our measurements improve. The expansion rate disagrees depending on how you measure it. The early universe appears more developed than it should. Subtle inconsistencies are beginning to accumulate. None of these alone are enough to break the model. But together, they start to form a picture where something is missing. One possibility is that there was an extra ingredient in the early universe. A brief phase where something behaved differently, altering how everything expanded before settling into the pattern we see today. Another is that the unseen components we rely on, the ones we use to explain most of the universe, are not quite what we think they are. We give them names, we describe their effects, but we still don't truly understand what they are. And that leaves room for something unexpected. What makes this moment so unusual is not that we've found a clear answer. It's that we've found a contradiction that refuses to go away. A situation where the universe is telling us two different things at the same time, and both appear to be true. That's not failure. That's the edge of understanding. Because this is how science moves forward. Not when everything fits, but when something doesn't. When the model almost works, but not quite. When reality pushes back just enough to force a deeper question. It's like working on a puzzle for years, confident you know the image, and then finding a piece that doesn't fit anywhere. You don't throw the puzzle away. You realize the picture you had in mind might be incomplete. And that's where we are now. The universe isn't broken. Our map of it is, and whatever comes next, whatever fills in these gaps, is likely to change not just how we measure the universe, but how we understand it entirely.